All right. All right. So what's going on today? So this I hope will be a quick video. It's meant to go over the set data structure in Python, and this is essentially the next data structure where I think pedagogically it would place somewhere after you've learned regular variables, you've learned tuples, you've learned lists, and you've learned dictionaries. Well, sets is a good next data structure to learn. And the cool thing is that you don't have to import anything to get this working, and it kind of fits into the Python syntax quite nicely. I mean, that's deliberate language design, but I'll just get into it right away. So how do we create an empty set? You can start off by saying, let's say I want to create a set of, let's see, letters, right? Just letters. So we can do that by doing this, and this is the empty set of letters. I could also do this. So letters set, and this is it's under this section about converting existing collections into sets. So here I could do A, B, and I'm just gonna stop at C, right? So here I'm converting A, B, and C into the set of letters. Now we get the same effect if we made this a tuple, right? That's perfectly fine as well. So this is how you create an empty set. This is how you convert an existing collection to a set. Now, thing is that sometimes when you, let's say I had a bunch of letters and I wanted to create a set out of it, these duplicate values would be removed. And well, the C and the A, and right, so you'd only end up with one of that. So let's print that out. Print that out. And so we see that you only have A, B, and C in there. And notice that the order in which that was presented was not in the order that I wrote these at all, right? And that's because sets are unordered collections of unique elements, right? And they are really good for checking membership, right? So if you have a collection of stuff and you want to efficiently check whether or not a certain thing is a part of that group, then sets are probably your go-to data structure for this. Okay, so what can we do with a set? Well, we can add items to a set. So let me add D to this. Let me add E to this set. And we'll just show that, right? So there we go. There's your set. So unique. Let's do it again. So that's unordered collection of unique elements. Fine. This sets is something you probably learned many years ago when you were, or I don't know who's watching this. So probably learned this in like primary school, right? Grade 3, 4, 2, whatever, about set membership. And so when you were learning about Venn diagrams and whatnot, so we can check if things are in the set. So let's do something here. I want to find out if G is in letters. Look how nicely that is, right? English. G in letters. This is gonna produce a Boolean value, true or false. Right. Let's do another one. Is A in letters. So what we're expecting is for this to be false and this to be true. Cool. False, true? False, true. Perfect. Perfect. We can remove members from a set. We could take stuff out. And there are a few ways to take things out of sets in Python. There is, and you can check the documentation for the distinction between these, but you can discard an item from a set. You can remove an item from a set, and you can pop. And the distinction here is that pop doesn't, as far as I know, take a value. You pretty much just say, you know, whatever the name of the set is, and pop, and it will remove a random member. Okay. And remove is like set.remove, and you remove an item, and it will remove item if item is in the set. If item is not in set, then you get an error about item not being in the set. So let me see what error we get a key error. Yeah. So error if item not in set. Right. Discard is a little bit more lenient, right? Discard item, it removes the item from set. If not in set, then cool. There's nothing to do if there's nothing to set. So let's do this. So right now we have a set and we have A through to E. So let's discard something. So let's do letters.discard, and G is not a member of our letters set. So nothing happens, right? No error. Let's try that here. And let's do a remove. There we go. We have our key error because G was not part of the set. However, we could do letters.remove A, and that worked. But let's print letters first, and there we have our set without A. Cool. Let's do pop, right? So right now our letters set has B through to E, and we're going to pop something off of our set and see what happens. So letters pop, right? And then let's print letters. There we go. So it looks like pop decided to get rid of D. Okay, let's run this again. It's supposed to be random. So what did we get? This time it got rid of B, and this time it got rid of B also. Cool. So the next thing that you can do with a set, and its proper terminology for this is what is the cardinality of the set? But this is pretty much just asking how many members are in the set, how many items are in the set, and Python uses its standard len function for this. So if we've removed A from our set, then when we try to get the size, we should have B, C, D, and E. So that is 4. Okay, so let's print the length of letters. And I just said 4, but we are doing 2 removes from here. So we get rid of A. So we have A to E. And it should be 3. It should be 3. So there we go, right? That's 3. Now, there are a few operations that we know that you can do on sets, like union, where that is everything that's in both sets, or all the sets that have been union together, so it's everything. And then intersection, which is the set of items that belong to both intersecting sets, or to the intersecting sets. Now, there are other operations that we can do with set, like the difference of a set, symmetric difference of a set. I'm not going to cover those here, because these are the most these are the operations that I've used most when I'm dealing with sets. I use difference quite a bit as well, but it hasn't come up that often recently. So let's union some sets. So let's do letters dot union, and I want to do Z, Y, X, and I am not going to pretend like it is trivial for me to like it's trivial for me to say my alphabet in reverse order. So I'm just gonna let that be. So this actually creates a new set. So this is front to, let me just call this front and back letters, right? And then I'm gonna print this. So here we should see our, well, we don't really know what we're gonna see, but we should see Z, Y, and X added to our set. And the reason why we can't predict exactly what we're going to see is because we have this random pop that's removing a set member here. So let's do that. And there we go. So it looks like pop decided to remove C. And so we have B, we have E, we have D, and then we have X, Y, Z. Cool. And we can take the intersection of sets as well, right? So if we do, let's say common letters. Okay, common letters is probably a bad name, but let's do letters, shared letters. There we go. And the reason why I decided not to use common is because, and not everybody I've come across uses this kind of terminology, but where I'm from, a common letter is a lowercase letter, right? But that's not what we're we're checking here. We're trying to see if two sets share members in what members two sets share in share. I'll try not to use the word common there. All right, so let's do letters intersection with let's create a set that has T, U, V, and a stray E, and a stray D, and a stray we might have a C. So let's do that. Okay, so let's print our shared letters, and this is what they had in common, right? So letters had D and E in common with this bit, this set that I created, and that's because C got taken out by pop. Okay, so those are the important set operations, or the frequently used set operations. You know, I told myself I'd do frequently used set operations, but honestly, pop isn't frequent. I feel like maybe I just felt like I should put that in there, but I don't pop, right? Remove and discard are more frequent. So where does this come up, right? Like I said, a set is an unordered collection of unique items. So whenever I have a problem and those characteristics are hinted at in the problem, where I need to do efficient membership testing, like does this thing belong to this group, or I need to find the unique items of some collection that may have duplicates, then that's when I'll reach for a set. Algorithms like breadth first search and other graph algorithms also make use of sets for checking whether or not states that and if you have no idea what I'm talking about here, just consider the video finished and continue doing whatever it is that you would want it to be doing. But in graph algorithms, when you're traversing the graph, there is a chance you might end up in previous nodes of the graph, right? And so to avoid that, you want to keep track of those nodes that you've seen before. And so you don't want to be added, you don't want to maintain a collection of two nodes that are the same, right? And you also want to have efficient check-in of whether or not the node that you are currently at is a member of the set of nodes that you've already seen or explored, right? So there you have two characteristics that scream out from the definition of sets and the definition of and the algorithms for traversing graphs, right? So that's that. I hope this was helpful. You know, if it was and you find this stuff useful, then by all means, hit subscribe, follow along, drop a comment, do all the stuff that people on YouTube do. All right, peace. That's a wrap.